Take a look at this string. It looks like harmless, but this simple line of text is actually a command that triggers one of the most sophisticated surveillance tools in the world. This is Predator, a mercenary spyware attributed to Intellexa. Like Pegasus, it infects iPhones, often using one-click exploits. The user visits a web page and boom, it turns the phone into a monitoring device. Hey, my name is Tony. You are on the Reverse Society channel, and today we are analyzing the surveillance framework of Predator spyware. It starts here. In the main function, the malware is a single binary with two responsibilities. On one side you have the watcher, and on the other, the helper. This is the surveillance worker we are analyzing today. Let's use a C++ representation here. First, it will create the helper handler object and initialize read and write kernel primitive. And then it starts the handler. Let's dive into this. Before diving into crusty mechanism of the spyware, I would like to mention a few pre-steps executed at the beginning of the start function. I won't detail each one, but the ending step. It calls nsget executable path to find where the binary is located on the disk. It checks the status and skips if non-zero. Otherwise, it will put the buffer filled by nsget executable path into the first argument of the handling function. The function is called. Now the implant is still on memory, but not on disk. The attacker wants to prevent file system-based detection. Once all this pre-work is done, a thread is spawned. And the spawn lambda will call a start Unix socket server function. This function articulates around two other functions, and I will try to explain what they do. First, we have the create listening Unix socket. Here is pseudocode written in C++. The function simply returns the socket's FD. Internally, it will use the classic socket and bind functions. Note that we have a local socket here, which means that there is no control server involved. So the question is, how a remote machine could communicate with that socket? My theory is that the watcher process will try to download a payload that bridges C2 commands to local socket messages, orchestrating the surveillance operation remotely. And finally, the helper will be able to consume messages from the C2 server. Once the socket is created, the accept function is called to catch the first connection request. Then it will loop over until it catches a connection and call the process client method. What the process client method does. We'll continue the execution, but just before, please, if you liked what we did so far, hit the subscribe button. When a command arrives, it reads the whole line into a buffer. Now, let's create a fake buffer representation for the rest of our research. It will get the buffer from the stack at offset 10 and set it as first argument. Then the hexadecimal value 2c is set as second argument, which is the ASCII code for comma. It will use as a separator for the split function. We know now that there is a comma that splits our buffer into two parts. Then the rest of the string will be split again with a comma separator. Now we have a better idea about the shape of the command. The split function returns the remaining part of the string. This last part is passed to the A to I function, so we can deduce that the last part of the command is a number. Now the return value of A to I will be stored in the register 23 and then passed as second argument. The integer 1 is passed as first argument. Then the calloc function is called, which means that the last part of the command is in fact the size of a buffer. We will update the fake representation with the value 128. The allocated pointer will be stored at register 20 and then register 24. Keep that in mind for the following code. Then it will continue to read from the socket. The first argument will be the FD of the socket. The second will be the buffer, and the third one the length. It will return the size of what has been read, and it will subtract that from the original size. If there is remaining bits to read, then it will loop over again. Now let's take a look at the command. We have to update it with our last findings. Let's remove that number. Now let's imagine that we have a payload of size 7, and let's continue the execution. We have another clue here. The first part of the command is passed to the A2I function, which means this is a number. Next, the process request function will be called. The first part of the command will be taken as second argument, the second part of the command will be taken as third argument, and the extra payload will be passed as fourth argument. Now let's recap what we have in terms of execution. Now we can add the process request method and inspect the content of the function. Now we can see in the first assembly instruction of that function that the second part of the payload will be checked against E, D or A. So let's update the fake string with A. And for each of these addresses we would like to see the code it points to. The first thing we can see is that A probably means init, and that the first part of the command is probably related to operation. And if we take a look at E now, we will understand that E means execute, and that the first part of the command is still handled as operation, and we see that the payload is passed to the execute function. And for D, no big surprises, it means did it. Now if we go back to the previous flow, we can add the following comments. Now let's trim our command representation. Great, now we still need to understand the meaning of this operation integer. As we saw earlier, we have three kinds of interaction we can have with operations: git, delete and new. Let's focus on the new operation code. It will help us to understand what kind of operation we have here. The new operation function simply starts with a validation check. We will use a C pseudocode instead. We'll see that it will subtract the operation identifier by 10, and if the result is greater than 3, it will skip. If we go back to the assembly code, we can see that the result is stored in the register 21. Keep that in mind for later. Now we have another hint. We know that we can only pass value between 10 and 13 included, and that we have only 4 operation identifier, 0, 1, 2 and 3. Now we'll touch to the code that would let us understand which kind of operation the Predator spyware actually does. The operation identifier will be stored in register 16. Then we will load the jump table into the register 17. It looks like that. Then the operation identifier will be used as an index of the jump table. For instance, for the identifier number 3, we will get that value. Now we set the register 17 to the current address of execution, and we use the offset from the jump table to compute the targeted address. In the disassembler at this address, I was able to see that it creates a shared pointer of the camera enable class. And then I did the same for each offset in the jump table. I was able to find these addresses and the class it belongs to. I was not able to do the full reverse of these classes, but my hypothesis is that the hidden dot suppresses iOS privacy indicators. The VoIP is about call interception. The keylogger is about capturing keystrokes. And finally, the camera enabler is about camera surveillance. Let's wrap up this command protocol. First, we have the operation identifier here, 13, which means 3, which means camera enabler. Then we have the command E, which means execute, and then the enable string, which is passed to the execute function of the camera enabler function. Now, if you want more details about this surveillance framework, I encourage you to read this article from the Reverse Society blog. I will drop a link in the comment section. And if you like iOS security and vulnerability research, I encourage you to subscribe to this channel. See you later.